All right, good morning, ladies and gentlemen. Let's get started. So, just another couple of nagging days to tell you to please fill out your course evaluations and a little bit about the final exam. So, indeed, I consider the final exam test 3 because this isn't necessarily a cumulative exam. The material that we be covered on test 3 is from November 13th to November 29th, so this Thursday. So the only major difference between the exams that you've been writing and the final exam will be there will be one more question. So you get half an hour extra time. We good to go? Get half an hour extra time. So there's time for one more question. Okay, so there will be questions, like detail type questions regarding, like I think we left off in terms of how blood carries oxygen and CO2. So there can be some detail questions around that. There can be some detailed questions around buffers, right? Because buffers are something new that we've kind of introduced and what compartments they're in, that type of thing. But then everything else is really around integration and problem solving, okay? That's what's the rest that we've been doing. So integration or problem solving around CO2 and oxygen. Oh, there was also detail around the sensors. That was the other thing that we haven't been tested on yet. Sensors regarding oxygen and CO2. So some detail around the sensors and the feedback system there. So I think that's the only parts where like you have to nestle down into some detail. The rest of it is all problem solving, okay? Changes in oxygen and CO2, how does that change ventilation? And then and then integrating ventilation with the kidney, okay? So how we're going to change, how we're going to get hydrogen ion messed up and how we're going to fix that. And then eventually on Thursday, how we get we have a whole body problem and how we use and how we get oxygen, CO2, mean arterial pressure, and hydrogen ion messed up, and how we go about fixing that. Okay? Are there any questions about the final exam? So really it's 3 weeks worth of work. Don't overthink this at all. There's no surprises come in. Okay? You're going to know exactly what this thing is going to look like. Okay? Read the question. Okay, this gets even more critical with integration. We're going to spend all Thursday on one example. Okay, that's a 500-mark question. So I have to be able to get you to do that type of activity for 10 marks. So I'm going to have to do something to focus you. So I might say, and we'll learn more about this on Thursday, but I might say, you know, you're losing blood. Tell me how that disrupts homeostasis. You tell me all about that. And don't worry, we'll go over that. So tell me how the body would compensate in the 10-minute ambulance ride to the hospital. Okay, so that's the 10-minute ambulance ride to the hospital is where I focused you right down onto anything that happens in milliseconds to seconds and anything happens in seconds to minutes. Okay, that means you're going to leave the kidney out of it. It's hours to days. So that's one way that I've tried to focus you down. Or in respiration section, I think in the last, on the last test 3, I've asked like a question about snorkeling. You're snorkeling in the Bahamas. Tell me the major compensation that's occurring in the body after a 3-hour snorkeling event. Okay, so you're going to focus yourself right down at the level of the kidney to tell me about how that major compensation is there. So time is something that I can use to help focus you down onto a certain pot of information. Okay, so just like any of the midterms, you've got to read the question, okay? And it becomes more important the more we integrate. Okay? Are there any other issues? Get off our chest about the final? Okay, well, if they come up, as they come up, funnel them my way and we'll talk about them, all right? Cool. Okay, so we were working through some examples of how we're going to get how hydrogen ion can be affected by respiratory disturbances. And so we did 2 examples very specifically where we had a respiratory disturbance. We saw how that affected hydrogen ion, and then we looked at buffer and renal compensation. Okay, so now we're going to look at how we might get hydrogen ion out of whack, not through the respiratory system, but just through specific acidosis or alkalosis. And then look how buffers in the lung might fix that. So then you've got every example of how the kidney might fix something, how the lung might fix something, and then we're going to put all of those together in order to see how the body would actually fix something, okay? So we left off, we did respiratory. Did we finish? Let me just make sure. I think we did. We left off, oh yeah. We left off with respiratory alkalosis, right? So we did hypo and hyperventilation. And so now we're going to get into some non-respiratory disturbances, what they call metabolic. Okay, so there can only be 2 of those. So let's get into non-respiratory disturbances. So this is hydrogen ion or CO2 or bicarb. HCO3 is altered directly. And they call these metabolic. Okay, so we had respiratory alkalosis and acidosis. Now we're going to go over metabolic alkalosis and acidosis. Okay. Okay. So I think we were on our 3rd one. So C. So let's go with metabolic acidosis first. So you can get yourself in, so this is just a way of adding hydrogen ion to the system directly, not through messing with CO2. So CO2 is normal, respiration is normal, but somehow we've messed now with the other side of the relationship, okay, bicarb and hydrogen ion directly. So you can get yourself into this situation by, let's say, excessive anaerobic metabolism. So you get that buildup of lactic acid, right? So you're adding acid to the system directly. You can have kidney problems. So at the level of the kidney, you've got either a hydrogen ion or a bicarb excretion problem. Okay, so maybe something going on down there. Okay, also can during pathological situations, so situations like diabetes or starvation, anorexia, those types of situations. Anytime where you start using fats and proteins as your primary fuel source, okay, from using that fuel source, you'll make ketone bodies, and these are acidic. So you will start to have a much more acidic environment if you're using fats and proteins as your primary fuel. So during diabetes or starvation. So situations where we're using fats and proteins as our primary fuel store or primary fuel source. That's how they spell fuel. Oh my God. Let's go with that. Fuel source. Okay, so then this creates ketone bodies. Which are acidic. Okay, so plenty of ways that we can actually increase the presence of hydrogen ion in the body, all right? But we can also have an increase in free hydrogen ion in the body if we were to decrease bicarb, right? If we decrease the amount of buffer, we go into some sort of base deficit situation, then we're going to have more free hydrogen ion. So the problem is really the same. Yes? Is there a Y in ketone? You're asking me about spelling. You know my history, and you're asking me about spelling. Somebody's got to Google that. You don't think there is? We're going to take a vote. No Y in ketone? No Y in ketone. Okay, we're good. Thank you. Right, increased hydrogen ion, decreased bicarb are the same challenge. Okay, I've been spelling ketone that way for 17 years. Just want to let you know. I'm comfortable with it. I'm comfortable now. Anyways, okay. I learned something today. Okay, so increased hydrogen ion, decreased bicarb are going to be the same thing, right? Because at the end of the day, if you had a decreased bicarb problem, the body doesn't fix a decreased bicarb problem, does it? The body doesn't regulate bicarb. Okay, so the body doesn't care about a decreased bicarb problem. When we're looking at these problems, we look at how does the problem that's presented affect hydrogen ion, because it's hydrogen ion that's regulated. Okay, that's a critical issue. All right, so we would ask ourselves then, what is this problem? Okay, so at the end of the day, if we think about our Davenport diagram, this is a problem that at the same CO2, so CO2 didn't change, there's no respiratory issue here. We have less bicarb, so that's like jumping down to a base deficit, okay? Get ourselves into a base deficit situation, so already you can start to see how the body might have to compensate to get ourselves back into the zone. All right, in terms of moving from one CO2 isobar to the next, so you can already start to get a feel for we might have to change ventilation in order to fix this problem. Okay, so this is just us busting our tools out a little bit. We think about our other tools. Henderson-Hasselbalch, where pH is proportional to bicarb over PCO2. All right, if we decrease the numerator, the number will get smaller, so we should expect pH to decrease. Okay, so the information is starting to head all in the same direction. Hydrogen ion, increased hydrogen ion is a problem, right? And then if we look at our equation, okay, so this is where I have to caution you. Okay, this is where it's really critical that we use this equation wisely. Okay, so for instance, if I were to tell you why we increase hydrogen ion, that was the problem, you're going to go, oh, I'm going to push the equation this way, right? We've been pushing this equation around for a while. But if I say, oh, we decrease bicarb, you're going to pull the equation this way. Both cannot be true, because that maneuver is illegal. Okay, this side of the equation is not changing. We said there was no change in respiration and CO2 is constant, so you can't pull it all the way over here or push it all the way over here. This side of the equation is not changing. Okay, respiration is keeping this constant at 40 millimeters of mercury. Okay, so you cannot do the maneuver of pulling it all the way. You can pull it a little bit of the way, all right? But the critical thing, though, is that you don't take a look at this and say, oh, bicarb's the problem, let's fix that. Bicarb is never a problem. Bicarb is a tool to fix a hydrogen ion problem. Okay, so convert any problem that we're having. So if on a test it shows up that suddenly you have a decrease in bicarb. That is not the problem. Convert that to a hydrogen ion problem. If I have less buffer, I will have more hydrogen ion. The problem presents itself. The problem tells you what it is. The problem is an increase in hydrogen ion. With respiratory problems, we had to convert a CO2 problem into a hydrogen ion problem. Here, the problem is presenting itself, okay? So we have an increase in hydrogen ion and a decrease in bicarb. They present themselves as the same thing. So at the end of the day, the problem is an increase in hydrogen ion or a decrease in bicarb. 3 negative, okay? So then we would look towards compensations for that. Okay, so if we think about our compensations, first line, let's think about them in terms of time. First line of defense is going to be our buffers, and we put that in equilibration with our hydrogen ion pool. And what were we paying attention to? Let's stay. We were paying attention to that unbound form. Okay, so if I have an increase in hydrogen ion, do I have an increase or a decrease in our buffer pool? We're going to have a decrease. So if I have an increase in hydrogen ion, we will push the equation in this direction because it can move. That's what buffers are for, right? So would we expect to see a decrease in that? Let's keep that separate. Decrease in that protein pool, right? Because we're binding it up. This is us minimizing the disturbance. Okay, we're hiding that hydrogen ion. So at the level of the lung, we have a problem here because we know based on the Davenport diagram that we do need a change in CO2, and a change in CO2 would really help us, right? If we could change CO2, but in order to change CO2, you have to provoke the system to change respiration. And at the moment, we have no provocation to do that. Okay, so it's these situations that got folks looking heavy into those chemoreceptors for CO2. Okay, so big debates as to what those chemoreceptors for CO2 actually measure. Okay, so we talked about those chemoreceptors for CO2. The relationship looked something like that. Okay, and we had a sensitivity of this relationship based on the presence of hydrogen ion, right? So there was already some ideas that this chemoreceptor is sensing hydrogen ion as well. Okay, so it turns out that the thinking at the moment is that these sensors monitor both, and that when you have an increase in hydrogen ion metabolically, right, so not through CO2, but metabolically, you will provoke an increase in ventilation. Okay, so it is absolutely true that this relationship exists. Okay, there's a huge amount of work to be done here, though, because there's still a fair amount of controversy over whether there is a separate set of chemoreceptors for hydrogen ion or whether we use the same one. But we can provoke it. Okay, so indeed, if we could provoke it then, and we would just read the graph, that increase in hydrogen ion would result in an increase in ventilation. Okay, so why would that be stimulated? Why is that going to help this situation? How does an increase in ventilation affect CO2? Can someone walk me through that? That's an old argument. How does an increase in ventilation affect CO2? Okay, work that one out. How does an increase in ventilation affect CO2? Yeah. Increased CO2 output. Okay, so how did you get yourself to an increase in CO2? So I'm just looking for the tool, like walk me through it rather than just giving me an answer. Like, how do we get ourselves to CO2? Yeah? So we've got an increase and a decrease. So absolutely, we're looking for trying to estimate what blood CO2 would be. In order to do that, we have to estimate what alveolar CO2 would be. And what tool did you use to estimate what alveolar CO2 would be? How did you get yourself there? So this relationship right here, right? The VA over Q relationship. It's critical as we work through any example that we justify. You know by now, in terms of how these things are graded, you cannot just give an answer. You got to justify how you got yourself there, okay? So indeed, if we work it this way then, if I were to increase my ventilation, my ratio gets big, so I tend towards infinity. So that would result in a decrease in PaCO2 and an increase in PaO2. Oxygen we're not too concerned about at the moment because it doesn't relate to hydrogen ion in any way, right? So why did the body go through this maneuver? Because now we've just changed this side of the equation, and now we can pull the equation in the direction that you want it to go. So, but we have to decrease it first. So we're going to go from like our 40 millimeters of mercury towards 20, right? So this is us popping back here to a different isobar, pulling the equation in this direction. Brilliant, but we had to change CO2 in order to do that first. Okay? And it's true that if we were to drop CO2, we would bind hydrogen ion and bicarb together to form the carbonic acid, and then eventually hide that hydrogen ion in the form of water, right? But as we decrease the hydrogen ion, we also decrease bicarb, right? Because we pulled it in this direction. So on our Davenport diagram, not only did we we decreased our hydrogen ion, so we came back to our normal pH. We dropped what appeared to be dropped buffer. This wasn't continued base deficit. This was just shifting forms. Okay, so you remember we got to keep track of when did we actually remove bicarb and when did we just shift forms. Okay, so this is just a manifestation of shifting forms. Okay, so a little bit of an addition here today. We can provoke a change in ventilation with a change in hydrogen ion. Okay? All right, are we comfy with that? Because then we'll go through the other example of metabolic alkalosis. So we could fix this with the kidney as well if the kidney wasn't the problem. So let's say you were a diabetic and you've been thrown into this situation, you could go ahead and fix this problem with the kidney as well. So my rules were we weren't going to fix it with the kidney, we were going to fix it with one thing. But you would know if you look back on your other examples, your other two examples, you can follow through how the kidney would work to fix this problem, and I would promote that you do that, okay? But what we need to get under our belt is the other fix to a metabolic problem now, how to get the lung going in the other direction, or helping us in the other direction, okay? So let's pop over into that example, metabolic alkalosis. What did I call that? CD. Okay, so this is a decrease in hydrogen ion or an increase in bicarb. Okay, it's the same problem. Again, we do not care about the problem of an increase in bicarb other than how it affects hydrogen ion. An increase in bicarb is base excess, so it is going to bind more free hydrogen ions, so we should see a drop in it. It's the exact same problem, okay? And the body won't care to fix it. So you can definitely get yourself into this situation by some sort of kidney malfunction. You can decrease hydrogen ion pretty quickly out of the body by vomiting. Okay, get rid of all of that hydrogen ion in the stomach space. We also have products that are alkali in nature, so you can actually that you can buy over the counter. So products that actually have bicarb in them to help, I think, settle an upset stomach. Or so you can actually ingest bicarb by mouth with over-the-counter products. Okay. So again, when we ask how does this affect hydrogen ion, the problem is presented to us very directly. Okay, in terms of what the problem is. So we don't have to go looking for the problem as much as we did when we were dealing with CO2. So essentially here we have no change in CO2, but we have an increase in bicarb. Okay, so that would be akin to firing up the 40 millimolar or 40 millimeters of mercury CO2 isobar, right? Because CO2 didn't change, ventilation hasn't changed. So that would mean our pH would go up and our bicarb has gone up. So it's akin to getting ourselves into a base excess situation. Okay. So again, you can already start to see how we might be returning ourselves back to normal and what ventilation is going to have to do, or CO2 is going to have to do to get ourselves back to the normal zone. If we think about our Henderson-Hasselbalch equation. We have an increase in our numerator, so we should expect to see an increase in pH. Okay, that totally jives with what Davenport would tell us. And if we think about our CO2 relationship, all right. Essentially, the problem was a decrease in hydrogen ion or an increase in bicarb. Okay, so the problem pretty much presents itself. We can't push or pull this equation around yet because we can't change this side of the equation. Right? We can't push or pull it until we can change CO2. We've got to provoke the system to change that CO2. Okay, so when we think about our compensations, all right, thinking about our compensations, milliseconds to seconds time scale. First is going to be our buffers. Okay, so what's going to happen here? Okay, I got it. What's going to happen with our protein buffer pool? Increase or decrease? With a decrease in hydrogen ion, how's that going to affect our protein buffer pool? Increase or decrease? Increase, because we're going to pull the equation in this direction, right? Minimizing the disturbance. We're going to our pool of buffer that has hydrogen ion already attached to it and stripping it off. We're minimizing the disturbance, okay? So indeed, we would then predict increase in that protein pool. Cool. So millisecond second time scale, minimizing disturbance. At the level of the lung, what's happening here? Take me through that. How would ventilation be provoked? And why would we do that? Increase in hydrogen ion. Yeah. So you're going to use the chemoreceptor graph that looks like this. Okay. And you're going to decrease ventilation. Okay. Decrease ventilation. How did that affect anything regarding CO2? So why was the body provoked to do that? Someone take me through that? Gonna give it a go? Yeah. So used VA over Q, brilliant. So this is akin to decreasing VA over Q. Awesome. So decrease ventilation, decrease the numerator so my number gets small. So I read the graph then and should see an increase in PaCO2 and a decrease in PaO2. Not caring too much about oxygen at the moment because it doesn't really affect or play into at all our hydrogen ion problem, all right? So an increase in CO2, increase in blood CO2, so that's going to be here, right? So how does that help us? That now helps us push the equation in this direction, right? To get hydrogen ion unhidden or unbound from the water form into carbonic acid and then into bicarb and free hydrogen ion, okay? So that is akin to moving, so we increase CO2, so from 40 millimeters of mercury to 60 millimeters of mercury, okay? So popping up this way to get ourselves back into the zone, okay? And indeed, with that increase in free hydrogen ion and a decrease in pH, we should also, we're pushing the equation in this direction, so we should see an increase in bicarb. Not because we are getting ourselves into a greater base excess, but because we just shifted forms, okay? So again, this change in bicarb is us shifting forms, okay? So base excess was the problem, but there is a shift in form once we fix the problem, okay? So it does seem a little weird, right, in a situation, this is where things get so confusing. It does seem a little odd that in an increased hydrogen ion situation, we would have an increased bicarb, right? That does seem a little odd, but boom, there it is for reals, okay? Cool. And again, the kidney could come in. If the kidney wasn't the problem, the kidney could come in and help fix this, right? We have an alkalization of the cells of the proximal tubule and the collecting duct, blah, 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 change transporters, good to go, okay? I'm not going to go through that. We've already gone through one of those examples, so bring that information forward here from respiratory alkalosis, and you'll have it nailed, okay? So now we've seen every problem there could possibly be and every solve there could possibly be. Okay, so now I'd like to combine them in order to start to think about how all these things are going to work together. Okay? Those are our basic tools to check to make sure we're in the right direction. There is a handout that kind of looks something like this that we're not going to go over. It's just the number forms of the graphs that we will be playing with. Okay, so I'm not necessarily going to go over those. For those that dig numbers, there they are. We are, though, going to tap into a second computer program that just deals with regulation of hydrogen ion, and it's going to give us the ability to look at changes in things that deal with hydrogen ion over time. Okay, so now instead of, in the respiration section, we looked at how things were changing over, let's say, 3 minutes, right? Because in respirations, it's on a more of a minutes time scale. Here, we're going to be adding the kidney to try to help us out. So we're thinking about days now. We're going to look at what's going on over 6 days. Okay. All right, so let's go over an example you're familiar with. So you've got some translatable information from what you've already done to what we're going to do now. All right, so let's go through hypoventilation. Oh, I got the wrong thing here. So hypoventilation, not enough ventilation. So this was our respiratory acidosis scenario, okay? And what we can watch here is ventilation, CO2, pH, and bicarb. All right, so we've got graphs that represent those. We have graphs that also represent acid production, so we'll get into that when we're thinking about a metabolic problem. And then acid excretion, that's kind of helping us with what the kidney's doing. Okay, so some indications about what ventilation is doing, some indications about what the kidney is doing. All right? Okay, and again, we're going to use these graphs just to check our work. You'll never be asked to reproduce any of these types of graphs on a test, okay? These graphs are just used to check our work to make sure that we're headed in the direction that we think we should. Okay, so do not think that you need to be able to reproduce these graphs. You need to be able to reproduce the problem solving behind them, but not necessarily the graphs themselves. They're just there to help us along the way. Okay, so the problem with respiratory acidosis is a drop in ventilation. So we've got a graph here that's going to tell us, indicates exactly what the challenge is, okay? Decreased ventilation. So at the end of the day, how does that disrupt homeostasis? Okay, that's the question we always ask ourselves when some sort of problem is put in front of us. If it doesn't disrupt homeostasis, and by homeostasis I mean regulated variables, okay, if it doesn't disrupt regulated variables, the body won't change, right? Obviously these graphs are showing changes, so something got messed up. So how does an increase in ventilation, decrease in ventilation disrupt homeostasis? Where are you going to start here? Decrease in ventilation, disrupting homeostasis. Yes. You're just rocking that VA over Q. That's awesome. Yes, absolutely. We've got ourselves into a decreased ventilation problem, so that should make all the little hair on your neck stand up to say, I got to use that graph. Awesome. So decrease in ventilation means my ratio is getting small. So I'm going to head in that direction. So indeed, that should be an increase in PaCO2 and a decrease in PaO2. Okay, at the moment we're focusing on the acid-base problem, so we're not going to focus too much on the oxygen right now. Okay? So then an increase in CO2, so there it is. We got an increase in arteriolar CO2. So we're on the right track. Okay? So how is that going to be affecting hydrogen ion? What tool are you going to use to try to get yourself comfy with that? Or does it? Doesn't, yeah. You're going to use the Henderson-Hasselbalch equation. Perfect. So we're going to go pH proportional to bicarb and CO2. We're increasing, so the number's getting smaller, so we should expect a decrease in pH. Awesome. There it is right there. Decrease in pH. Okay. We could also use the equation. Okay, because we have an increase in CO2. We're going to push the equation in this direction. So we should fully expect an increase in hydrogen ion. Okay, there's our regulated variable. A increase in bicarb. And an increase in hydrogen ion is going to be a decrease in pH. So in terms of our Davenport diagram, this is kind of a little truncated. Davenport diagram here. Okay, we're looking at getting ourselves out in that direction. Okay. So compensations. Oh, 1, 2, 3. Yeah, so that we've got a bicarb graph. Let's check on our data. So we've got hydrogen ion coming down. That's perfect. Bicarb going up, okay? That's us shifting forms. That's not the kidney doing anything yet. Okay, so that's the shifting the forms. So if we were measuring bicarb, we would see it go up. We're shifting forms. Okay. And then at the level of the kidney is doing something right away. This is interesting. The kidney is doing something right away. It's increased, so we have an increase in acid excretion, right? So that's just the kidney doing what the kidney does. We have an increase in acid in the system, so we're getting an increase in filtered hydrogen ions, so we're getting an increase in excreted hydrogen ion. That's just the kidney doing what the kidney does. Okay, so it's not renal compensation yet. It's too early, right? Remember, kidneys were hours to days in terms of fixing a problem, right? That's just the kidney doing what the kidney does. All right, so in terms of compensation, let me write that down just to make sure everybody is clear that this little piece is we are filtering more. So we're excreting more. Okay, kidney doing what the kidney does. All right, compensations. Okay, compensations. Go through these in terms of time. What are you going to do first? Buffers. Awesome. So that's our milliseconds to seconds time scale. What's going to happen with our protein pool then? Increase in hydrogen ion. Got it. What's going to happen with that pool? You're going to decrease it because we're going to push the equation in that direction. Increased hydrogen ion, we're going to bind it, minimizing our disturbance, right? So if I push the equation in this direction, I'm going to have a decrease. Brilliant. On our minutes time scale, minutes to hours time scale, would be the lung. At the moment, the lung is the problem, right? So the body would certainly try to fix with the level of the lung, but it's not going to work because the lung is the problem, okay? Okay. So then on our hours to days time scale, what's going to happen? Increase hydrogen ion, increase bicarb. What are we going to do? The level of the kidney. What do we have the capacity to do? Yeah. Sorry, say that again? Hemoglobin? So we're, I guess so the kidney doesn't actually have the capacity to increase hemoglobin, right? But what can the kidney do with hydrogen ion and bicarb? You can, absolutely. So in order to fix this problem, we can increase hydrogen ion excretion, increase bicarb reabsorption. How did that happen? How did the body get provoked to do that? Yeah. Brilliant. So absolutely, we got to provoke the body to do it. So it is that acidification. Acidification of cells of the proximal tubule and the collecting duct, and then fill in the rest of that answer, which was you are going to increase the number of transporters on certain cells on the luminal side for hydrogen ion and the interstitial space side for bicarb, okay? And so know a couple of examples of what those transporters are. You're also going to change enzyme activity, right? So take all that information that we learned from earlier in your respiratory acidosis example and plunk it right here. That's where it fits, okay? Brilliant. So let's just make sure, increase hydrogen ion excretion. So 5, 6, so indeed, now we start to see the kidney do renal compensation. Okay, so a really high excretion, increased bicarb reabsorption. So indeed, we're starting to see our cells get into a base excess situation. Okay, 7 is down here. Cool. And based on that, even though ventilation is still depressed, right, the pH problem will be resolved. Okay, so this is the kidney can fix the problem. Okay. So problems, so in terms of our Davenport diagram, we went to, actually there's other bicarb lines here, we popped up to a base excess bicarb line. At the same CO2 because we didn't mess with ventilation in this example. Okay, the next example we'll go over, we will do both, okay? And we're just going to do as many of these examples as we can get through today. Hopefully we'll get through at least 2 more. Okay, let's take a quick break and then we'll pop back into those. Oh, I'll leave that up. Okay guys, let's get back at another example where we actually see all the compensations at the same time, or to help out with our problem. So in our example of ketone production, oh look at there, it's spelt right there. Dang. Anyways. So this was our example that again we've done before. So we can bring that information forward here. Increased ketone production, so this would be somebody in an elevated state of utilizing either fats or amino acids or proteins as fuels, right? So that's our metabolic acidosis. Essentially then the problem is an increase in acid production. So the problem presents itself in terms of how we disrupted a regulated variable, right? So we have a graph of acid production right here. Okay, so there's our challenge. With an increase in acid production, obviously, then we should see a decrease in pH. We have an increase in acid production. We have an increase in free hydrogen ions, so we will be using bicarb as a buffer to bind it, right? So we should expect to see a decrease in bicarb, right? This is not renal compensation. This is bicarb being a buffer, right? And we should expect to see an increase in, since we've got an increase in acid in the system, immediately on a very early time scale, we should see the kidney filtering more acid, therefore excreting more acid. So this is just the kidney doing what the kidney does, not renal compensation yet. Okay, so we should see that increase in acid excretion. Increase in acid excretion. Okay. So if we think about our situation, CO2 plus. All right, indeed, we already know that we have an increase in hydrogen ion, which would be a decrease in pH. That was presented to us. Decrease in hydrogen ion would create a decrease in, or a decrease in CO3 negative, okay? So that was 2, and that was 3. For those following along with numbers. Okay, so metabolic acidosis and alkalosis tend to present the problem pretty directly. We'll use our little Henderson-Hasselbalch equation, or sorry, our Davenport to see where we're at. Same CO2, get ourselves into something similar to a base deficit. Okay, so we got ourselves into this range. That's our problem. All makes sense. Okay, so then this one we can absolutely bust out all 3. Okay. So all 3 compensations. So where do we start? With our first compensation. Do it in terms of time. What do we do first? Buffers. Cool. What's happening here with our protein buffer pool? Increase in hydrogen ion. So decrease. So we push the equation in that direction, right? So we should see a decrease in our buffer pool there. Perfect. at the level of the lung. What would be happening here? Increase hydrogen ion. Is that going to provoke the ventilation system to do anything? Increase ventilation, so how'd you get there? Chemoreceptor. Perfect. Okay, so why did we do that? How's that going to help us with a hydrogen ion problem? Yep. In front? Yeah. V over Q. Cool. Increase VA over Q makes my ratio big, so we head in that direction. So we get an increase in PaO2 and a decrease in PaCO2. Okay. Brilliant. Why did we do that? Decrease in CO2 now allows us to pull the equation over in this direction. All right, now that we've changed ventilation, we can change CO2. All right, so that should help us hide that excess hydrogen ion in the form of water. But we should expect to shift forms of bicarb when this happens, right? Let's check our work here for a minute. We were at 1, 2, 3, 4. So this would be 5. Increase in ventilation. Bam, there it is. Okay, and our CO2 should have gone down. Ooh, there it is. Okay, so that's our decreased CO2. We got it. And then we would start to shift forms of our bicarb. Before we head there, let's think about what the kidney's then going to do. So our third line of defense, here's the kidney. Okay, third line of defense. What's happening at the level of the kidney? My problem is an increase in hydrogen ion, decrease in bicarb. What's the kidney doing overall? Nothing. Okay, we'll leave it there. We have no idea what the kidney's doing, and we'll move on to another example. What's the kidney doing? Yeah. So we're going to increase hydrogen ion excretion. Perfect. And you know how that got provoked to do that? Perfect, so we changed the transporters, but how did we provoke them to change the transporters? Acidification. Got it. All right, so we got to provoke the system to do it. So increase the acidity. Of the proximal tubule and the collecting duct, and indeed you would follow that up with an examples of what transporters would be increased and on what side, and enzyme changes and what that would do in terms of production. Okay? So we indeed are increasing bicarb reabsorption, okay, and we're increasing bicarb production because we're increasing that enzyme. Okay, so if we were to increase bicarb reabsorption and production, okay, when we do look at, where are we at, 6, increase acid excretion, you said, so there it is, happening, renal compensation. Okay, we're increasing that acid excretion even more. All right, and then when we go to bicarb, okay, we are increasing bicarb reabsorption. And so we still see it low. Okay, and this is ultimately the crux of one of the problems of MDs measuring bicarb in the blood and trying to figure out what's wrong with humans. So indeed, if we had a graph that measured bicarb production, it would go like this. If we had a graph that said bicarb production, it would be going way up. But we don't have a graph that says bicarb production. We have a graph that says what is the bicarb level in the blood. So this bicarb that we are making, we are using. We have an acid problem, it's a buffer. So we are using all of that we are producing, right? So when you measure it in the blood, you actually see a drop, or that it's maintained low, but now it's maintained constant, okay? But if we were to actually measure bicarb production, it would be way up. It just so happens that it's the buffer that we're using to help us with the hydrogen ion disturbance, right? Because the problem never went away. It wasn't an acute problem. This was a problem that stayed over 6 days, so we are continuing to fix it over 6 days. So critical here, right, is that whatever we're doing has maintained our pH within the zone that we're comfy with, and we're constant. Okay? So we've stabilized the body. It might not be exactly where it wants to be, but we've stabilized the system. Okay? So the system will stabilize out at whatever production of bicarb production is going on at the level of the kidney, because we've stabilized the problem. And essentially when you do multiple compensations, which this is an example of exactly how the body would respond. We did some contrived examples before about breaking the body with one problem and fixing it with another. Okay, those were contrived examples. This is exactly how the body would respond or would try to respond. Okay, and when it comes then to the Davenport diagram, it's a little bit weird because it wasn't a single problem and a single solve. Right? So you actually, when you wander back into this region, we did change CO2, right? So we did change CO2 levels. So we did come back a little bit, but then we started over time to add buffer, right? So that would have popped us up to another buffer line, and then we continued to change CO2. So we kind of have this zigzag pattern as we move from base excess lines and CO2 lines, right? So multiple compensations pull us back to our zone, but we move a little bit on one front, move a little bit on the other, move a little bit on one front, move a little bit on the other to get us back, okay? So it's not just the single compensation that we talked about before, both compensations are represented there. So we change a CO2 line, we change a buffer line. Okay, so you come back in kind of the zigzagged pattern because now the body is using all of its tools available in order to fix this problem. Okay, and that's exactly how the body would respond. Okay, so on any question that you see, don't leave one out because I left one out early on in our discussion. Okay? Try to assess whether the body would have all the things available to compensate and what it would do to do that. Okay, so we're not going to have time to go over any other examples, but the other examples we've gone over already. So C was an example of altitude. Okay, so that's an example we've already done, so we're just going to re-go over that one. But we were going to add the kidney component. Okay, I'm totally comfortable if you can do this, that you can totally then use that altitude example as a way of flexing your muscle and studying. We've already done the acid or the oxygen CO2 piece of it. Now we're just take the CO2 piece and carry that on into hydrogen ion. And the fourth example we never get to anyways, so it's not really an important one, okay? I would definitely go over the altitude example. And on Thursday, we will go over an example of a whole body question, okay? We'll put it all together, okay? Cool, we'll cut it there then.